Well, good morning. Welcome to the Renkus-Heinz booth. Thank you for coming. I'm Rick Kirby. I'm the Vice President of Sales and Marketing at Renkus-Heinz, and I'm going to spend the next 15 minutes or so talking about our ICONYX digitally steerable array technology. Here's a brief overview of what we're going to cover. We're going to talk about ICONYX, which is a steerable line array. We're going to discuss a little bit of the theory behind them. Fairly light-hearted, lots of pictures, nothing too technical, no math certainly, or I wouldn't be presenting it. Why steerable line arrays are a useful tool, why they have a benefit in fixed installations, the technology, how we do it, why we think we do it better, and then there's some examples of our success stories. These steerable line arrays that you see here, I like to call it the new old technology. There's a lot of people come into the market now having invented this technology. But if we look back in Olson's book from 1957, you can see that line arrays were certainly understood and described in his book back then. And beam steering also. Steering was explained in Olson's book from 57 by using delay to tilt and steer away from. So it hasn't just been invented. Quite like this quote, the ancients keep stealing our ideas. But there is some new things. The ability for us to actually design and manufacture these things has been a big change. We now have cost-effective multi-channel amplifiers that we can fit inside these columns. We have computer control to do the math, powerful FIR filters and DSP engines, and also higher power transducers. So we've been able to move it from theory into a real product with some real benefits. So now the boring bit. We're going to have a quick look at how multiple sources interact. In our ICONYX columns, we have a continuous line of 4-inch concentric drivers, and the spacing between them is very important. We're just going to start by looking at two drivers. If I take two components and put them close together, if I put them in fact within quarter of a wavelength of each other, the output of those two devices appears as though it's coming from a single source. They get very little directivity, but there's very little interference between them. And this is the same as when you were at school playing with a ripple tank and little dippers in the water. You can see the way these wavefronts would combine and interfere or create single flat wavefronts. If we increase that spacing to half a wavelength between them, they take on some directivity. We start to beam. We get rejection above and below them. Open it up to one wavelength, and we end up with a main beam, and then these top and bottom lobes, and open it up to two wavelengths of spacing, and we get some very awkward interference. So we need to avoid this with our line array. And that's the way all line sources work. This spacing between the drivers defines your high frequency control limit for the array. And the length of the array, the height of the array, controls the low frequency limit. So the next slide shows us here directivity versus the height of the array. And we can see here, if our array is short compared to a wavelength, if it's, in this example, half a wavelength tall, we get very little, if any, directivity. As the array approaches one wavelength tall, we actually take on some quite good pattern control. 2 wavelengths tall, we create a very tight beam. 4 wavelengths tall, an even tighter beam. And this goes up and up as the length of the array compared to wavelength becomes longer. So we can now create from this line a very tight beam. But how do we use it? Why is this useful? Well, we're going to start by looking at an example here, a typical church. A very typical church. This is modeled in ease, and we can see the green areas here are our seating areas. And we've put some loudspeakers in here to simulate the effects of the ICONYX system versus a traditional solution. The church is you can see it's got a 3.5 second RT60 in the mid-band. It's a fairly typical room, plaster walls, a wooden ceiling, and empty wooden pews when we're modelling it. And we've put 2 loudspeaker systems in here. At the top, we've hung 2 traditional horn systems. They're quite large horns, and we've got a 60 by 40 horn to do far throw, and a 90 by 40 horn to cover the near field. And then the bottom red arrow is pointing to one ICONYX speaker mounted on the wall. Now, just to give you an idea of how big these speakers actually are, this is the horn. It's a 2 foot by 2 foot horn. Next to it is our ICONYX, which is a 12 foot tall column in this particular case. And next to it is our production manager, who's 5'2". And if we look at the directivity balloon for the horn, this is at 500 hertz, at 1 kilohertz, at 2 kilohertz. It's very good at being a horn. That's pretty impressive for a horn, 2 foot by 2 foot. So the sound goes where we point the horn. That's a good device. But when we compare it to ICONYX, this is the directivity balloon from an ICONYX column at 500 hertz. You can see straight away that we've got much, much more control. We have a much higher Q beam. There's ICONYX at 1 kilohertz, at 2 kilohertz. And we have the benefit in ICONYX of being able to steer it electronically. So with the computer plugged in, we can steer where that beam goes without having to physically angle the column or the speaker. And this is us looking straight into an ICONYX speaker. You can see how it's steered and coming down on top of the audience area. The direct SPL, the coverage from the horn system. Well, most of the energy is in this yellow space on the floor here. We can see that. But we've also got quite a lot of energy hitting the ceiling here, and that's going to create reverberation. Remember, the room's got a 3.5 second RT60, so it's going to bounce around, echoes, and it's going to make it quite unintelligible. Compared to the ICONYX, where obviously all of the energy is on the floor, we have very little hitting the reflective surfaces. And just toggling between those two, you can see straight away our direct to reverberant has shot up dramatically with ICONYX. So we put a whole lot less energy into the space, and we're covering the seating area more evenly with ICONYX. We're going to look at a method of measuring that. We can simulate ALCONs, which is a measure of intelligibility. And with the horn system, this is the ALCONs for the room with the horn system. Not terrible on the floor. Actually, it's about as good on the ceiling as it is down there. But compare that to the ICONYX. Very clearly with ICONYX we get excellent intelligibility over the audience area, over the intended area, and that's as a direct result of this controlling the beam and putting it on the people rather than letting it rattle around the space. And if we look at the statistics for that, the horn system gives us this top graph, which is barely acceptable to some of the people, and ICONYX is giving us very good to excellent for 100% of the people. So higher directivity gives us better intelligibility. If we're able to control the sound, stop it leaking into the space where we don't want it, we get better intelligibility. So that's why it's a good idea. That's why this product is beneficial. We're now going to have a little look at how we do it. Now, ICONYX is different to many of the other solutions out there. We have a continuous line of 4-inch coaxial drivers. And we have this coaxial high frequency array in the middle. Every single one of those drivers has its own amp channel and its own DSP built into the loudspeaker. In these columns here are IC16s. We have a continuous line of 16 of these drivers. So there we have 16 drivers, 16 amp channels and 16 DSP channels controlling it. And we can control the frequency response, the delay, and everything to do with those drivers on a driver-by-driver basis. One other nice thing about having a coaxial driver is we maintain horizontal consistency as well. If we just had a single full-range 4-inch driver, at about 4 kilohertz, that driver's only 60 degrees wide. The lobe really collapses, and it gets narrower and narrower as we go up in frequency above that. But by using our two-way, this coax with the high frequencies, we keep the high frequency nice and wide, all the way up to 18 kilohertz. So here's an example of that. This is the coverage of a 4-inch full-range component, and then you compare that with ICONYX, 150 degree coverage versus that 60 degrees. And that's real. When you're in the extremes of an ICONYX, it's still very tonally consistent. And we have this very broad horizontal, very, very tight vertical. because we can build columns very, very high. In this case, I call this a 16. This is built of 2 8-element modules. We go up to 4 tall, which becomes our 12-foot or 4-meter column. Now, another one of the myths out there with these steerable columns is you see people with short little arrays claiming they can get a 5-degree beam. Well, they have the same laws of physics to deal with as we do. And the laws of physics dictate that in order to get a 5-degree beam out of a product, it has to be 14 wavelengths long, at the wavelengths that we're interested in. We can't change that, that's just the way it is. So arrays with small, tiny sections like this of high frequencies can't develop that at the frequencies at 1 kilohertz. There's no way they can. You need a tall column. And what you see if you look at our literature for the product is we define the area of beam control improves as the column gets longer. So in the short ones we can get control to around 800 hertz. In the very tall ones we can take that down to 200 hertz. I've also touched on the fact that we have a continuous line, this consistent driver spacing, and that allows us to move our acoustic beam anywhere on the column. If we had a fixed high frequency section, we have to put the high frequency beam where that section is. With us, we can move it up and down the column wherever we want. We can even create multiple beams on it. And we have our own technology, we call it constant lambda, for controlling the consistency and the tonality within this beam. Here's an example of how we use constant lambda to taper the array to get us a beam on the center of the column. If we put all of the frequencies to all of the drivers, you would end up with something that had extremely high directivity at high frequency, and as you go down in frequency and the wavelengths get longer, it's going to open up. And that's not very useful to us. We don't want something that's 1 degree at 10 kilohertz. So we use all of the array at low frequency and progressively less and less of it as we go up in frequency by filtering on the individual drivers. So here at 4 kilohertz you can see we're using 3 drivers and maybe a little bit from their adjacent ones. At 2 kilohertz we're using 6 drivers, and we do that tapering throughout the whole array. And that gives us a result that is pretty consistent within the intended coverage area with frequency. We don't have a laser beam at high frequencies and uncontrolled beam at lower frequencies. It does a pretty good job. Now here's a simulation of this beam we just saw centered in the middle of the column. Because we have this continuous line of drivers, we can actually do that tapering to anywhere on the column. So here's the same thing, but we're now tapering to the bottom of the array, and that will result in a beam centered towards the bottom of the array there. And we can do the same by tapering to the top of the array, and we get a beam at the top. We can actually use this to create beam centers anywhere on the column. So I could have one here, I can create another beam at the bottom, one in the middle, depending on the application and the challenges we're trying to overcome. So being able to move this beam center up and down the column is a big advantage. It's critical for how we design and install these. If you can get it at the right height, you can have a much narrower beam and keep it just on the people. Again, improves intelligibility. If you put the beam way up high and try and point it down to cover the same area, you have to have quite a broad beam, and straight away you've got more leakage, I suppose, for want of a better term, into the space and more reverb. So make the beam low, you can keep it nice and tight, nice high Q beam, improved intelligibility. There's some other benefits. By being able to move the beam up and down the column as part of design, we can put it above people's heads, or if the contractors installed the column at the wrong height, we can move the beam electronically instead of having to explain to the pastor that we need to drill more holes in the wall. We can also use it to control reflections off the back wall. So if we're in a space and we notice we're getting some strong reflections, we can move the beam a little bit higher and point it down a little bit, and now the reflections are going to go into the floor rather than back at the presenter. So we've got a quick example of a room with a low ceiling here. typical ballroom with a 15-foot ceiling, and we want as tall an array as possible to maximize intelligibility. We want to keep a nice tight beam, and we want that to the lowest frequency we can get. So we've put the column on the wall here, and you can see here, if we had a beam fixed at the bottom of the product, you have a number of problems. You're hitting the microphone, so you've got no headroom before feedback. If our friend at the back stands up, he shadows the people behind him. So an array with a center fixed at the bottom is not the best idea in this particular example. So here's an example with the beam centered in the center. We're getting a little bit better. We get a bit more gain before feedback. We've still got quite a strong reflection off the back wall. And if our friend stands up again, he's again causing shadowing. But if we had a product where the beam is fixed in the center, that's the best you can do. With ICONYX, because we can slide that beam all the way to the top, we can now bring it down above the head of the presenter. We've got better gain before feedback. We have a better angle into the back wall so that it reflects down into the floor, less shadowing, and good even coverage. So we're not compromising. Now, with ICONYX, we could do it anyway. We could do it in any of those three examples. But we can do that, we can move it up and down. If we'd chosen a fixed center, as some people have done, all they can do is that one or that one. So that's a benefit to our continuous line. And I said earlier we can do multiple beams. Well, here's an example where I have 4 beams. I've created 3 beams for the floor, 1 for a balcony. Here again, 4 beams, but now I've chosen to hit the balcony from an acoustic center at the top of the column. So less compromise, and that beam now from the top of the column can be tighter. One other thing we would notice is if you do have to mount the column too high, for architectural reasons, for example, it is better to use multiple very tight beams than it is to use one broad beam. You get much better control by using more high Q beams than one single low Q beam. The bleed out of that is much worse than this arrangement. To set up and program these is very simple. We have an Ethernet-based network. We call it our Rayon network. You can just plug into the product. It pops up in the computer. You design your beams here. You can simulate. You can draw the room from within the Rayon software. And here you can see creating multiple beams, moving the centers up and down. And we can even affect the relative level of those beams from one to the other to maintain the best coverage and consistency from front to back. Our Rayon software also allows you to network many loudspeakers together, and we can deliver audio to them over CobraNet, AES EBU, analog. We can equalize them within the software. We can use time delay to take care of any alignment issues. And also we supervise all of the loudspeakers in the network. We actually measure the impedance of all of the components, and we supervise it. We can send emails if there's a driver failure or an over temperature event, and we can prove the system integrity at any point. So far we've discussed the traditional ICONYX product, the white one you can see here. This technology has now developed into a product we call IC Live. We have an example here, which takes this technology to a much higher output, more live performance-based system. And instead of small little 4-inch components, we've gone up to a 6-inch. We've got proper compression drivers in there, and we get the ability to still create tight beams and steer them, but much higher output, much more musical for proper rock and roll applications, conferences, corporate events, where they may have talking heads during the day, speeches and shareholder meetings, but then they have a party band at night, and they need to use this system for the band as well. We have it in a fixed installation version, and there's an example showing you the components that we use. This array of high frequency compression drivers there, and our 6-inch woofer. Most recently, we've expanded this technology again to the product just over there, the IC² product, and that's a very new product for us. be shipping sometime early next year, and that takes this technology into even larger arenas, larger theatres, where we can now hang up many, many boxes, in this case up to 8 boxes currently. So that's the technology of ICONYX, how it works, why it does a good job. One final thing I want to show you is one of the most important things with ICONYX is its aesthetics. Certainly when we're trying to deal with architects and persuade them to let us put loudspeakers in a room, it disappears. There's actually ICONYX on the wall there, and there you can hardly see them. This is how loudspeakers used to be installed. Yep, that's real. This one's my favorite. And with ICONYX, we're doing it very neatly within the architecture. So there's ICONYX in the columns in this space here. You can barely see them, but there's one there, and you can see it in the inset over there. Here's a church, and with their traditional solution, this is a before and after, so they have a cluster of loudspeakers here, and I guess they figured it wasn't quite covering well enough, so they stuck a few more there and there. Their old system, obviously they weren't happy with it because they asked for it to be replaced, and we replaced it with ICONYX. ICONYX there and there. Much nicer, much more sympathetic to the architecture. Community of Christ Temple, very nice. Clearly an architect was involved in this. It's a lovely room. We have 2 ICONYX covering this space, one on either side. We have one beam for the floor, one for the banked seating, and one for the balcony. And if we look at the room the other way, there they are. So just 2 loudspeakers covering the entire space, and very sympathetic to the architecture. This is also a great product in highly reverberant spaces like big old echoey cathedrals. In this picture here we can see the legacy system. They're old column arrays that were on every column, delayed down through the space. And here you can see the system that replaced it was an ICONYX. We have them in mass transit applications, for example LAX Airport, intelligibility and PAVA applications. Here's a cathedral in Montreal, covering all of this space with an ICONYX on either side there. No need for these delays that you see. Train station in Stockholm, where again it's being used for paging. Cathedral of St. Peter, ICONYX mounted nicely on the columns there. And we don't have to have all of these delays the whole way down through the church. Auditoriums, another church. This is a university installation here. There's a couple of ICONYX there. They blend in very easily. We also have people that mount them within the walls here, so you can see it's hidden behind a scrim inside the structure. This is a particularly interesting project in Norway, where we have lots and lots of ICONYX installed, and they can flip the room around for different applications and split it up into different spaces. And we can go on and on and on. So one final project I want to just show you, because it's such an interesting one. It's a church called Padre Pio in Italy. It's a 6,500 seat church. There's a person there you can see for scale. Massive, massive space. Lots of glass, very difficult acoustically. And we cover all of that with 2 ICONYX. One there and one there. They cover the whole room, 6,500 people from 2 loudspeakers. So, there you go. That was ICONYX. How it does what it does and where it's used. You would add subwoofers for playing music, yes. So ICONYX itself does very well for light music, maybe a man with acoustic guitar, vocal, but just add a subwoofer for some low-end reinforcement. ICONYX will go down to about 80 hertz, but if you need to get output, if you need to get high output at that level, add a subwoofer and cross them over a bit higher, maybe 120. and it does a very good job. We have actually, one of the slides we have here is an opera environment where there's 6 of these IC16s in this room, and it's used for opera. Okay, well, thank you very much. We're going to be giving presentations throughout the show every day. There's an agenda on the video monitors over there, so see if there's anything that interests you and come back and see us. Thank you.